Ask an assistant about a document on your own computer, a contract, a report, something written this morning. It has never seen it. It was trained months ago on text that did not include your files, and it has no way to go and read them. So it will either tell you it cannot help, or it will do something worse and produce a confident answer about a document it has never read. This is not a flaw you fix by making the model bigger. A language model's knowledge is fixed at the moment training stops. Everything it knows is already inside its weights, and your private files were never in there, and neither was this morning. Making it larger gives it more of what it already had. It does not give it your contract. This is the math behind. Today, how an assistant looks things up. The two you have probably used work this way. ChatGPT from OpenAI, run by Sam Altman. Claude from Anthropic, run by Dario Amodei. Both companies were founded by groups rather than by one person, and the specific arrangements differ. But for this video, the interesting thing is that the mechanism underneath both is the same, and it is not complicated. The fix is to let the thing look something up before it answers. Find the handful of passages most likely to contain the answer, paste them into the prompt above your question, and let the model reply while looking straight at them. That is the whole idea. It has a name, Retrieval Augmented Generation, and it is much less clever than it sounds. So we need to find the right passages, and to do that we turn text into numbers. A model reads a passage and produces a long list of numbers, a few hundred to a few thousand of them, that stands for that passage. Do it once, in advance, for every passage in your files. Then do it to the question when somebody asks it. Now, closeness. Multiply the first number of the question by the first number of the passage, the second by the second, all the way down, and add up everything you got. That is the dot product. The larger it comes out, the more alike the two pieces of text are, and if you scale both lists to the same length first, that single number is all you need to rank every passage you have. Which sounds finished, and is not, because of a detail that turns out to be the whole engineering problem. You do not have 6 passages, you have 1,000,000, and somebody is waiting for an answer. Every one of those 1,000,000 passages needs comparing against the question, and it needs doing before the person gets bored. Count it honestly. 1,000,000 passages, each a list of 1,536 numbers. Comparing the question against all of them is 1,536 million multiplications. 1.5 billion for one question from one person. Now imagine 1,000 people asking at once. This is the part that has to get cheaper. There are 2 ways to make it cheaper, and both are worth understanding. Make the lists shorter, or stop comparing against everything. Take the lists first, because the mathematics there is genuinely surprising. There is a result from 1984 by William Johnson and Joram Lindenstrauss, and it says something that ought to be false. Take any collection of points in a space of any number of dimensions. You can squash them down into far fewer dimensions, and every distance between every pair of points survives to within a tolerance you choose in advance. And here is the part that should stop you. How far down you can squash does not depend on how many dimensions you started with. Not at all. It depends only on how many points you have, and how much distortion you are willing to accept. 1,000,000 points behave the same way whether they started in 10,000 dimensions or 10,000,000. But I want to be careful here, because this theorem gets quoted to justify something it does not justify. Put the real numbers in. 1,000,000 points, 10% distortion, and the bound demands 11,842 dimensions. Real systems use 1,536. The theorem is asking for nearly 8 times more than anybody actually uses. So why does 1,500 work? Because the theorem promises something stronger than we need. It holds for any set of points at all, including ones arranged by an adversary to be as awkward as possible. Real passages are not adversarial. They are not scattered evenly through the space, they lie close to a much smaller surface inside it, and the effective number of directions that matter is far lower than the number of coordinates. Now the second idea, and this is the one that actually makes search fast, stop comparing against everything. Pick a few thousand representative points and assign every passage to whichever one it is nearest. Now the space is divided into cells. When a question arrives, find which cell it lands in, search that cell and a few neighbours, and ignore the rest of the million entirely. Most systems now do something better. Build a graph. Every passage becomes a node, joined to a few of its neighbours, and crucially some links are long, crossing the whole space in one hop, while most are short. Start anywhere. Look at the neighbours of where you are. Move to whichever is closer to the question, and repeat until nothing nearby is closer. Long links first, so you cross the space in a few jumps. Short links at the end, so you arrive precisely. 1,000,000 passages is about 20 doublings, and a walk like this touches a few thousand nodes rather than 1,000,000. That is the difference between a query costing a second and a query costing 9 milliseconds. And now the honest part, because there is a word doing a great deal of work here. Approximate. You are no longer guaranteed to find the closest passage. The walk can end in the wrong neighbourhood, and the cells can put a good answer just over a boundary you never searched. It is measured, not hoped for. Of the 10 genuinely closest passages, how many did you actually find? 95% of them, in 9 milliseconds, is a better product than all 10 of them in a second. That is a real engineering decision, and it is made deliberately. It also means that when a system like this fails to find the right passage, nothing has gone wrong. It did what it was designed to do. There is a third trick, and it is the one that makes the memory bill survivable. 1,000,000 lists of 1,500 numbers stored precisely is several gigabytes sitting in memory. So do not store them precisely. Chop each list into short pieces, and for each piece keep only the nearest entry from a small catalogue of typical pieces. You are storing a rough sketch of every passage instead of the passage itself, and the sketches are small enough that comparing against all of them becomes cheap again. And because everything so far has been approximate, most serious systems add one honest step at the end. Take the 50 passages the fast search returned and score those 50 properly, with a second model that reads the question and the passage together, rather than comparing two lists of numbers. It is far too slow to run on 1,000,000. On 50 it costs almost nothing, and it reorders the short list into something much closer to right. So the passages come back, and here is what actually reaches the model. Your question, with a few thousand words of retrieved text pasted above it. That is all. The model is not told which parts were retrieved, or how confident the search was, or whether it found anything good. It sees text, and it answers from the text in front of it. Which is not quite what the original paper described. The 2020 paper that named this idea treated the retrieved documents probabilistically, weighting the answer across several of them at once. Almost nothing in production does that. Real systems paste the top few passages into the prompt and let the model sort it out. The published method and the deployed one-parted company almost immediately. Which tells you exactly how this fails. If the search returns the wrong passage, the model answers confidently from the wrong passage because it cannot tell the difference. That is why the characteristic failure of these systems is not a refusal. It is a wrong answer with a citation attached to it, and the citation is real, and it does not support the claim. So, text becomes lists of numbers. Closeness is a multiplication and a sum. And because 1,000,000 comparisons is too many, you either shorten the lists using a theorem that promises far more than it needs to, or you build a graph and walk downhill through it, accepting that you will sometimes miss. The model at the end is doing something impressive. Finding the paragraph is the part that had to be clever. Thank you for watching. Subscribe, and see you in our next video.